Good morning, students. Today I will discuss about the operational amplifier. An operational amplifier or an op-amp is very high gain differential amplifier with high input impedance and low output impedance. Operational amplifiers are typically used to provide a voltage amplitude changes, oscillator, filter circuits, etc. An op-amp may contain a number of differential amplifier stages to achieve a very high voltage gain. This is a high gain differential amplifier using direct coupling between the output and the input. This is suitable for DC as well as AC operation. Operational amplifier perform numerous electronic functions such as an instrumentation device, signal generator, active filter, etc. Besides various mathematical operations, this versatile device is also used in many non-linear applications such as voltage comparator, analog to digital converter, digital to analog converter, logarithmic amplifier, and non-linear function generator, etc. There are the following characteristics like input stages. This is the first stage and has the following characteristics: high CMR. CMR means common mode rejection, high input impedance, wide bandwidth, and low DC or input offset voltage. Following are the two inputs to the differential amplifier. V1 is equal to non-inverting input, V2 is equal to inverting input. Look here, the basic block diagram of operational amplifier. There are three stages. In first stage is the input stage, second stage is intermediate stage, and third stage is output stage. In input stage, there are differential amplifier and constant current source are available. And an intermediate stage differential amplifier, emitter follower, and level shifters are there. And output stage is output. The characteristics of operational amplifier. The important characteristics of parameter of an operational amplifier are as follows: open loop voltage gain, output offset voltage, common mode rejection ratio, and slew rate. And construction of operational amplifier and op-amp consists of differential amplifier, level translator. I have discussed about this. Look, the focus on characteristics of operational amplifier. First one is open loop voltage gain. The open loop voltage gain of an operational amplifier is its differential gain without any feedback path. Mathematically, the open loop voltage gain of an op-amp is represented as AB is equal to V0 upon VID. V0 upon V1 minus V2. VID is equal to V1 minus V2. Second one is, note that output offset voltage. The voltage present at the output of an op-amp when its differential input voltage is 0 is called an output offset voltage. VID equal to 0. V1 minus VID is equal to 0. That means V1 minus V2 equal to 0. That is implied to the V1 equal to V2. This one is the output offset voltage. Third one is very important point: common mode rejection ratio. Common mode rejection ratio of an op-amp is defined as the ratio of the closed loop differential gain AD and the common mode gain AC. CMR is equal to AB upon AC. Note that the common mode gain AC of an op-amp is the ratio of common mode output voltage and the common mode input voltage. Slew rate. Slew rate of an op-amp is defined as the maximum rate of change of output voltage due to the step input voltage. Mathematically, slew rate can be represented as SR is equal to maximum of dV0 upon dt, where V0 the output voltage in general. Slew rate is measured in either voltage per microsecond or volt per millisecond. Types of operational amplifier. There are two basic types of operational amplifier. First one is ideal op-amp and second one is a practical op-amp. Look at the diagram of circuit diagram of ideal op-amp. There are some characteristics of ideal op-amp. Input impedance should be infinite. Output impedance should be 0. Open loop voltage gain should be infinite. Bandwidth is infinite. Common mode rejection ratio is infinite. Slew rate is also infinite. Look the diagram of ideal op-amp. That means ideal op-amp does not have any internal current. Practical op-amp. Practically, op-amp are not ideal and deviate from their ideal characteristics because of some imperfection during manufacturing. The equivalent circuit of practical op-amp. The op-amp is shown here the following figure. This one is the practical open. Look at the diagram, students. There are following characteristics of practical open: input impedance Zi in the order of mega ohm, output impedance Z0 is the order of few ohms, open loop voltage gain AB will be high. When you choose a practical open, you should check whether it satisfies the following conditions. First one is input impedance Zi should be as high as possible. Output impedance Z0 should be as low as possible. Open loop voltage gain AB should be as high as possible. Output offset voltage should be as high as low as possible. The operation bandwidth should be as high as possible. CMRR should be as high as possible. Slew rate should be as high as possible. Note that all that points. There are the following characteristics of practical open. You can choose the practical open. You should check whether it satisfies or not. Next, open can be used in a both linear and non-linear applications. The following are the basics applications of open. First one is inverting amplifier. Second one is a non-inverting amplifier. Third one is a voltage follower. Now we discuss about the inverting amplifier. Look at the circuit diagram of inverting amplifier. Here, inverting amplifier takes the input through its inverting terminal through a resistor R1 and produce the amplified version as the output. Look the diagram. Now, note that for an op-amp, the voltage at the inverting input terminal is equal to the voltage at its non-inverting input terminal. Physically, there is no short between these two terminals, but virtually they are not short with each other. In the circuit shown above, below, the non-inverting input terminal is connected to the ground. That means 0 volt is applied at the non-inverting input terminal. The nodal equations apply to this terminal: 0 minus Vi upon R1 plus 0 minus V0 upon Rf equal to 0. That is it. That calculate the output voltage V0 is equal to minus Rf by R1 into V1. That is equal to the AB is equal to V0 upon Vi. That is also called the voltage gain of inverting amplifier. It must be is equal to the minus Rf by R1. Note that the gain of the inverting amplifier is having a negative sign. It indicates that there exists a 180-degree phase shift difference between the input and output. Second one is non-inverting amplifier. A non-inverting amplifier takes the input through its non-inverting terminal and produces its amplified version as the output. As the sum suggests, this amplifier just amplifies the input without inverting or changing the sign of output. Look here at the circuit diagram of non-inverting amplifier. Here we apply the input to the non-inverting terminal. Then how to calculate the voltage gain of the non-inverting amplifier? We apply the two conditions, virtual short concept and apply the voltage divider rule. First concept, voltage at the non-inverting terminal is equal to the voltage at the inverting terminal. So if we consider the Vi is the voltage at the non-inverting terminal, so we put the here V1 voltage. Look at this. V1 equal to V0 upon V0 into R1 upon R1 plus Rf. According to virtual short concept, the voltage at the inverting input terminal of an op-amp is same as that of the voltage at its non-inverting input terminal. That is equal to the V1 equal to Vi. V1 is equal to V1 क्या है? V1 यहाँ पे V1 equal to है V0 into R1 upon R1 plus Rf equal to Vi. V0 upon Vi निकालेंगे तो V0 upon Vi equal to R1 plus Rf upon R1. That is equal to V0 upon V1 upon equal to 1 plus Rf by R1. Note that. Now, the ratio of output voltage V0 and the input voltage Vi or the voltage gain of the non-inverting amplifier is equal to the 1 plus Rf by R1. Note that the gain of the non-inverting amplifier is having a positive sign. It indicates that there is no phase difference between the input and output. Voltage follower. A voltage follower is an electronic circuit which produces an output that follow the input voltage. It is a special case of non-inverting amplifier. If we consider the value of feedback resistor RF as a 0 ohms, the value of resistor 1 is infinity ohms, then a non-inverting amplifier becomes a voltage follower. Look at the circuit diagram. In the above circuit, the input voltage Vi is directly applied to the non-inverting input terminal of the op-amp. So the voltage at the non-inverting input terminal of an op-amp is equal to the Vi. Here the input is directly connected to the inverting input terminal of an op-amp. Hence, the voltage at the inverting input terminal of an op-amp is equal to the V0. According to the virtual short concept, the voltage at the inverting input terminal of an op-amp is same as that of the voltage at its non-inverting input terminal. That is equal to the V0 equal to Vi. So the output voltage V0 of a voltage follower is equal to the input voltage Vi. Thus, the gain of the voltage follower is equal to the 1. Since both the output voltage V0 and the input voltage Vi of the voltage follower are the same. Note that point. Gain of the voltage follower is equal to the 1. Next, summing amplifier circuits. The electronic circuit which perform arithmetic operations are called arithmetic circuit. Using op-amp, you can build basic arithmetic circuits such as adder and subtractor. In this topic, I will learn about each of them in detail. Adder. An adder is an electronic circuit that produces an output which is equal to the sum of applied input. An op-amp based adder produces an output equal to the sum of input voltages. Adder means that ये दो voltage को add करता है, दो या दो से ज़्यादा voltage को op-amp circuit में. It is also called as a summing amplifier since the output is the amplified one. The circuit diagram of an op-amp based adder is shown. This one is the adder circuit, adder op-amp circuit. This is also called as the summing amplifier. In the above circuit, the non-inverting input terminal of an op-amp is connected to the ground. That means 0 voltage applied to its non-inverting input terminal. According to the virtual short concept, the voltage at the inverting input terminal of an op-amp is same as that of the voltage at the non-inverting input terminal. So the voltage at the inverting input terminal of op-amp will be 0 voltage. Where nodal equation applies 0 minus V1 upon R1 plus 0 minus V2 upon R2 plus 0 minus V0 upon RF equal to 0. That is equal to V0 equal to minus RF into V1 upon R1 plus V2 upon R2. If R1 RF equal to R1 equal to R2 equal to R, then the output voltage V0 equal to minus R into V1 upon R plus V2 upon R. That is equal to V0 equal to minus of V1 plus V2. This one is the summing output of adder. Therefore, the output based adder circuit discussed above will produce the sum of the two input voltage V1 and V2 as the output. When all the resistors present in the circuit are the same value, note that the output voltage V0 of an adder circuit is having negative sign, which indicates that there exists a 180-degree phase difference between the input and output. Note that. Second one is the second subtractor circuit. Second summing amplifier circuit is the subtractor. A subtractor is an electronic circuit that produces an output which is equal to the difference of the applied input. An op-amp based subtractor produces an output equal to the difference of the input voltage applied at its inverting and non-inverting terminal. It is also called as a difference amplifier. The circuit diagram of op-amp based subtractor circuit is shown in this figure. Here, V1 and V2 two input voltage are applied. R1 is the input connected to the V2. R2 is connected through the V1 and R3 is also connected and through the ground. RF is the feedback resistance. Now we find the Expression for a output voltage V0 for the above circuit using superposition theorem. Step first, firstly, let us calculate the output voltage V01 by considering only V1. For this, eliminating V2 by making it short circuit. Then we obtain the modified circuit diagram is shown in the figure. इसको शॉर्ट सर्किट करने के लिए इसको अपन को ग्राउंड कर दिए. Now using the voltage division principle, calculate the voltage at the non-inverting input terminal of an op-amp VP. Here we consider VP, so VP is also here. VP is equal to V1 R3 upon R2 plus R3. Now the above circuit look like a non-inverting amplifier having input voltage VP. Therefore, the output voltage V01 is equal to V01 equal to VP into 1 plus RF by R1. Substitute the value of Vp in the above equation. We obtained the output voltage V01 by considering V1 as V01 is equal to V1 R3 upon R2 plus R3 plus into R1 plus RF by R1. This one is the question number 3. Step 2. In this step, let us find the output voltage V02 by considering only V2. Similar to that, in the above steps, eliminate by V1 by making a short circuit. The modified circuit diagram is in the figure. You can observe that the voltage at the non-inverting input terminal of the op-amp will be 0 volt. It means that above circuit is simply an inverting op-amp. Therefore, the op-amp voltage V02 of the above circuit will be V02 equal to minus RF by R1 into V2. This one is the question number 4. Now, after that, step 3. In this step, we will obtain the output voltage V0 of the subtractor circuit by adding the output voltages obtained in step 1 and step 2. Mathematically, it can be written as V0 equal to V01 plus V02. Substituting the value of V01 and V02 in the above equations, we get the V0. तो यहाँ पे V01 और V02 की वैल्यू पुट करेंगे. जैसे ही V01 V02 की वैल्यू पुट करेंगे और RF इक्वल टू R1 इक्वल टू R2 इक्वल टू R3 इक्वल टू R पुट करने के बाद V0 जो आएगा that is equal to V0 equal to V1 minus V2. Note that this one is the difference between the input voltage. Output voltage equal to the difference between the input voltage V1 minus V2.